This comparison illustrates the massive gap in modern aerospace economics. On the left, NASA's traditional cost model estimated $3.6 billion to develop a new rocket. On the right, SpaceX built the Falcon 9 for $390 million, a fraction of that cost. This tenfold reduction resulted from a hostile rejection of standard manufacturing protocols, rather than a breakthrough in thruster physics. Psychologists call the underlying problem addition sickness. Musk's first move was a massive error, the alien dreadnought. He attempted to fully automate the entire factory floor from the very beginning. The complexity broke the line. First pass yield, the number of cars coming off without defects, fell to 14%, forcing massive crews of humans to manually rebuild every vehicle. After months of sleeping on the factory floor, Musk realized his instinct to lead with robotics was entirely backward. From that failure, he established the algorithm's most rigid requirement, the sequence. By mandating that automation must come absolutely last, he encoded the lesson of the Model 3 into the core of his companies. Step 1 is to question every requirement. Musk uses the idiot index, a metric showing that rockets cost 50 times more than their raw materials, to argue that most aerospace costs come from inherited, unquestioned military specifications. Step 2, delete any part or process you can. To ensure engineers are being aggressive enough, Musk demands they eventually add back at least 10% of what they removed. In 2018, SpaceX scrapped expensive carbon fiber for Starship in favor of industrial stainless steel. That deletion dropped material costs 50 times and removed the need for paint and heat shielding, as steel handles re-entry heat better. While traditional lean manufacturing focuses on reducing waste within a process, radical deletion questions the existence of the process itself, triggering cost collapses that standard optimization simply cannot match. Only after questioning and deleting does the framework move to steps 3 and 4, simplify and accelerate. These are only applied to the components that survived the deletion phase. Tesla's gigacasting replaces over 70 individual steel and aluminum parts, and the hundreds of welds required to join them, with a single massive casting. This shift reduced rear floor costs by 40% and turned a multi-hour welding process into a 2-minute cycle time. Only then do you reach step 5, automate. Violation of this sequence usually leads back to Musk's battery pack story, where a robot was struggling to glue fiberglass acoustic strips onto the cells. Musk first tried to fix the robot. Only later did he revert to step 1 and ask what the strips were for. When tests showed they didn't actually reduce cabin noise, he deleted the strips, the robot, and the entire supply chain. This sequence prevents the most common error in engineering, the drive to optimize a component that should not exist in the first place. Tesla's production trajectory reflects the algorithm's cumulative impact. Between 2017 and 2023, annual vehicle deliveries grew from roughly 100,000 to over 1.8 million, a 17.5x increase in 6 years. This chart shows the collapse of launch costs. During the space shuttle era, it cost over $54,000 to put a kilogram into orbit. Today, a reusable Falcon 9 has brought that figure under $2,000. But the framework operates as a blunt instrument. By design, it treats necessary safety buffers and redundancies as waste to be deleted. At Twitter, applying the algorithm led to an 80% staff reduction and the reckless unplugging of server racks. The resulting platform outages and glitchy broadcasts showed that in complex software, redundancy is often a requirement, not a flaw. Applying a hardware deletion framework to social infrastructure exposes a fundamental fragility. When a system depends on deep connectivity, aggressive subtraction can break the very thing it is trying to save. The algorithm has also reached its limits in safety-critical hardware. When Musk ordered the removal of radar and ultrasonic sensors from Tesla vehicles to rely solely on cameras, the result was an immediate uptick in crashes and near misses. Tesla was eventually forced to quietly add high-resolution radar back into its new cars. This move proved that the algorithm's acceptable 10% error rate for deletions is dangerous when human lives are the variable. There's also a severe human cost. Maintaining this pace requires 60 to 90-hour work weeks that chew through engineering talent, limiting the average employee's tenure to just 5 years. This raises the question of whether the framework can survive without its creator. Competitors like Jeff Bezos's Blue Origin have immense resources, but lack the same urgency. Without the constant threat of bankruptcy to drive it, the algorithm may be too brutal for most organizations to adopt. The sequence forces a confrontation with foundational questions before an engineer begins optimizing the wrong answers. Yet, as the failures in software and safety show, this brutal sequence may only be survivable when driven by one person's extreme, costly willpower.